The next talk will be given by Lucy Goodacre from King's College in London, and you may know her being one of the faces of the New Researcher Network as well. She holds a Master of Pharmaceutics from the UCL School of Pharmacy and is currently doing her PhD at King's College, where she looks into advanced experimental and computational methods to optimize nasal drug delivery with a specific focus on nasal mucus simulants, which could be used to study mucus drug particle interaction in the nasal cavity. And she'll touch upon a topic which has been mentioned earlier several times, and this is how to actually code a nasal cast for deposition studies using this nasal mucus simulant. So over to you.
Thank you very much for the kind introduction. I hope you can all hear me okay. Yes, so I'm Lucy. I'm doing a PhD at King's, and I'm in my third year. And today I'll be talking to you about how we can evaluate nasal mucus simulant application to the Aeronose Nasal cast specifically for nasal deposition studies. And just not to dwell, because I know it's been spoken about in depth, especially by Julie, but just kind of a bit of an overview for the nasal cavity. So you've got the nasal valve towards the anterior region, you've got the turbinates, which you target for systemic, the olfactory for nose to brain, and then the nasopharynx towards kind of the posterior region. And nasal casts, which are basically 3D models of the nasal cavity, are commonly used to evaluate a regional nasal drug deposition. However, what's common throughout all these different types of nasal casts, so you've got the Koken cast, for example, the Alberta idolized nasal inlet, for example, and the Aeronose, which I'm specifically going to be talking about. And what's common with these casts is that they're very difficult to coat with something that kind of represents kind of the mucosal lining. So what I've planned to do and what I've developed is a nasal mucus simulant at the start of my project to try and coat these casts with. And hopefully we can see some difference between kind of the current methods, so the simple coating methods like the glycerol ethanol, glycerol bridge, and water, to see whether kind of these complex, like a complex mucus containing mucins, something that represents the more rheological properties of nasal mucus, whether this has an effect on kind of nasal deposition. So just to quickly take you through the Aeronose cast, I know also most of you will be aware of kind of how this works, but it's got different blocks. So again, anteriorly, you've got the nasal valve, and then kind of the turbinates in the middle for blocks kind of 3 and 4, and then towards the back, the nasopharynx. So my objective that I set out was to produce a liquid that can line the cast and gel in situ, and kind of undergo that like liquid to gel transition in the cast, line the cast reproducibly, form a continuous film, and also be removed after the experiment as well to make sure that each experiment is reproducible. So I had to think about how would be the best way to achieve this, and I looked at different polymers, and I came across a polymer called Pluronic F127, which is also called Poloxamer 407, which is a brand name. And this is a tri-block polymer, so you've got 2 polyethylene oxide groups, which are hydrophilic, and a polypropylene oxide group in the middle, which is hydrophobic. And what's interesting about this polymer is that it's thermosensitive. So if you put it in the fridge, it'll behave as a liquid. If you leave it at room temperature for 10 minutes, based on the concentration, and a lot was done to kind of just to figure out which concentration was best to use, and in the end, I went with 18%, and I can explain why. But like I said, if you leave it at room temperature for, say, 10 minutes, it will then form a gel, and it actually gels to the consistency of mucus based on the rheology studies that I've done. And this is kind of a bit of background to kind of how this works. So you have the PPO group, which will become less soluble and kind of start to aggregate, and it forms a micelle kind of structure, which gives rise to kind of the semi-solid structure that we see. And you can see with the kind of temperature sweep, not to kind of dive too much into rheology, but you can see that G prime and G double prime, or the storage and loss modulus, as you wish, as this increases, it basically means gel strength increases. So you can see with temperature, if you increase temperature, you're increasing the G double prime at a certain point after gelation hits. So this means that we can kind of use this mechanism to kind of coat the cast. We can apply the mucus as a liquid. It will then gel in situ in the cast. And this is also reversible. So if you cool the mucus back down, it then comes back to a liquid, which means it's easier to wash out of the cast. So a bit about kind of simulant manufacturing, kind of how I made this mucus. And like I said, this was this was done over the course of the first year of my project, so I'm happy to talk to you more about that over lunch if you want to know kind of how I produce this and why I use specific concentrations. But I first dissolved 2% weight mucin type 3 in a simulated nasal electrolyte fluid, which is basically a buffer containing sodium chloride, potassium chloride, calcium chloride dihydrate. And I heated this to 37 to kind of help with the mucin dissolution. I then stirred this overnight. I then cooled it down to 4 degrees to then dissolve the 18% weight pluronic, which is really, I cooled it down to make sure that kind of the viscosity didn't increase too much and it helped with the dissolution. And then I stirred this overnight as well and stored it in the fridge. And also to mention, I added 0.5 weight fluorescein for the imaging studies that I'll come on to later on. So I developed 5 different methods for coating, and I wanted to kind of see which was the best way to get this mucus into the cast, to make sure that it was uniform, to make sure that it was reproducible, and that it kind of formed a nice layer in the cast everywhere. So 5 different methods. I started off with pipette and brush separately, and this was done while the cast was kind of disassembled, so I had each of the different blocks of the cast. And I applied 5 milliliters of mucus, either using a pipette or brush. I then also tried to nebulize the mucus, and I'll come on to kind of a bit about the data behind the nebulizing of the mucus. But I used 2 different types of nebulizer, mesh and jet. And then I also tried a fill technique where the cast was kind of assembled as one big block, and prior kind of been in the freezer to kind of cool the cast down to kind of help with the mucus distribution in the cast. And then I applied either 20 or the 50 ml fill of the mucus in via the nasopharynx. Kind of tilted it all around for 5 minutes, poured out the excess, and then disassembled the blocks, left them at room temperature for the mucus to gel in situ. And like I said, I applied fluorescein, so I kind of I used a lumina, which is basically a fluorescence imager, and I gave kind of each of the blocks a region of interest across each of the blocks. And you can see what's common, where mucus is present is red, and where mucus is not present, it's just clear. And especially with the pipette and with the brush techniques, you can see, especially with blocks 2 and blocks 4, that we're not seeing a continuous kind of uniform distribution of the mucus inside the cast at all. There's lots of gaps, which is obviously not ideal. Whereas you compare that to the 20 and the 50 ml fill, and you can see that it's a lot more uniform inside the cast. So what I did was I wanted to take forward these best 2 kind of fill techniques and analyze these more quantitatively. So I compared the intensity of the region of interest across the different blocks and compared the 20 and the 50 ml fill technique. And you can see two-way ANOVA, these are significantly different in terms of blocks 2 and 3 especially. We're seeing a difference between kind of the intensity in these blocks when I compare these 2 techniques together. And also to mention that the range for the 50 ml fill technique was a lot smaller, again, which meant it's more reproducible. So we could basically deduce from this that the 50 ml fill technique was better than the 20 ml fill technique in terms of coating the cast more uniformly and reproducibly. So a bit about washing the cast. We wanted to make sure that after each experiment that we conducted, that the cast was washed properly. There was no mucus left in the cast. So what we did was we submerged each of the blocks of the cast in ice-cold water, and 1.5 litres of ice-cold water, which again is acting on that reversibility of the pluronic, going back to a liquid, more easily able to come out the cast, basically. And then we dried them with an air gun. And we then re-imaged the cast and compare this to kind of background intensity. And we can conclude from this that the background intensity basically matched the intensity of the clean cast, and that there was no mucus left in the cast, basically. Yeah, as you can see here. So a bit about transferability. Like I said, this technique is specific to the Aeronose cast, which is here. I wanted to also have a look at a different cast, which I know is commonly used in the literature, which is the Alberta idealized nasal inlet. And what I found is when I tried to conduct the technique in the same way with this different cast, is that the 50 ml was it's too high of a volume, basically, to be added to this cast. It overflowed the cast. It clogged up all the intricate parts of the cast, which would later have an effect on how we conduct these regional deposition studies. So what I did was I halved the volume and required and inputted this into the cast, basically. So just to mention that the process of the pluronic, so having it be a liquid at cold temperature and it then gelling to the consistency of mucus at room temperature, this will happen no matter what cast is used. So the process, the mechanism can be applied no matter what cast is used. It's just the quantity will need to be kind of adapted depending on what cast you're using, basically. So a bit about kind of the perspective of this and kind of why this is important, and why we want to put mucus into the cast, and kind of is it having an effect, is kind of what I'm conducting at the moment. So in collaboration with Nanopharm, I'm conducting a design of experiments to look at 2 different types of formulation, a powder and a liquid, in different casts, in both the Alberta and the Aeronose cast, and looking at different types of coating. So comparing those kind of simple techniques that we're using at the moment, the water, the glycerol, ethanol, etc., and comparing that to kind of the complex mucus that I've developed to see if these coats are having an effect, if the different types of coats are having an effect on regional deposition. To see if the effects are the same for powder and liquid, which is most likely that they won't be because there's lots of literature about kind of the difference between these formulations. Seeing if airflow impacts deposition. I know this was mentioned, especially by Phil earlier on, kind of the importance of airflow and how this may have an impact on where the drug is going and how the drug may interact with mucus. And if these findings are translatable across the 2 different types of cast, the Alberta and the Aeronose. So just to quickly conclude, a mucin gel coat has been developed that can be applied as a liquid that will gel in situ, undergo liquid to gel transition in the cast, line the cast reproducibly, and that can be removed after the experiment as well. So I just want to thank all these wonderful people for all of their help. I wouldn't be able to do this research without them. Thank you as well to the DDL committee for the opportunity to present this to you. And yeah, I'm happy to answer any questions. Thank you.
Thank you very much for this great talk. So there is an immediate question.
Jan-Olof Svensson, AstraZeneca. Can you elaborate a little bit about the possible influences from this coating agent if you are assessing the amount of drug captured in the casts? What about interferences in your UPLC systems when quantifying the...
Yeah, that's a very, very good question. And I had to run a study basically without any drug just to kind of see if there's an impact with my peak. So the drug that I'm using is sumatriptan, and I know the specific retention time. So I wanted to make sure that the mucus that I was using in this cast, especially with the mucin included, if it had any effect with the peak and how I would end up analyzing the drug. And there was no influence basically. So I was happy that to kind of go on and conduct these studies with the deposition, with the mucin there, because I knew it wouldn't have any impact on how I'd eventually quantify the drug. But yeah, very important.
Does it influence the recovery in general terms as well?
The recovery, I'm not seeing too much of an impact on recovery at the moment. There's a couple that I had to redo. I usually kind of set myself a cutoff of about 75% in terms of the mass balance. But I'm not finding that having too much impact. I'm kind of evaluating the data as I go along. So I'll have more kind of to talk about, I guess, in the new year once all the data's been analysed. But at the moment, I'm not seeing too much of a problem.
Good. Thanks a lot.
No problem.
Lucy, could you comment
Yes.
on the, let's say, kinetics of the of your polymer of the gelation? So how quick does it gel if it gets to room temperature?
Yeah, so at room temperature, what I normally do, especially once I disconnect all of the blocks, because it's already formed the film, and there's such a small quantity, it only takes about 10 minutes once it's reached room temperature to kind of set in place, which is really, really good. You don't want to be waiting around for ages for the thing to gel. Obviously, if you have a bulk amount of the mucus, it will take longer, but because I'm obviously pouring it in as a liquid, then disassembling the blocks, because it's such a small amount lining the cast, that you're finding that it's not taking very long at all.
Thank you, Lucy, for the nice talk. Did you somehow evaluate the thickness of the film and if that is homogeneous in your cast?
Sorry, would you mind repeating the question? I can't quite hear you.
The thickness of your film throughout the cast.
Yeah.
Did you evaluate that or if it's homogeneously?
The thickness,
yes,
sorry.
exactly.
Yeah, the thickness. So thickness is a really important question and one I really wanted to answer as well during this talk. And I actually went to Aptar to conduct some X-ray tomography experiments to actually have a look at the mucus thickness to see if we could actually benchmark the in vivo mucus thickness, which is actually it's around like 50 micron basically, which is quite small. And unfortunately, due to the sensitivity of the equipment, we were seeing that even if we actually coated the cast and that we could see that mucus was actually in the cast, we couldn't actually detect it on the equipment. So it was such a shame because I wanted to kind of show you some nice images of the tomography, and you can see like the thin layer of the mucus and quantify like how thick it was. But I guess that's still kind of ongoing and maybe a limitation to the study that I've done. But yeah, very, very good point.
So there is another question related to one of the methods, because I think in the results you mostly showed the pipetting and the brushing and then the different
Yes,
amount
the
of liquid.
yeah.
So what about the nebulization? Can you comment on that?
Sorry, I forgot to mention that. Yeah, so nebulization would have been a great technique because what's done at the moment, especially at Aptar, is they nebulize water. So it'd be great to have a mucus to nebulize to kind of compare the difference. And when I tried to nebulize, because of the viscosity of the mucus simulant, even if I cooled it right down to kind of make it a liquid, it couldn't nebulize, basically. The surface tension and the viscosity was too high. So I don't know if there's ways of improving the nebulizer to see if we can nebulize viscous solutions. That might be an option. But unfortunately, I didn't have any data to go with the kind of nebulized technique that I did. Yeah.
Maybe you could also comment on the need of a complex mucus simulant, because I think aside of that study, you're working on mucus simulants most closely mimicking what you actually see. Is that actually needed in a cast study, or is it just about being sticky?
Yeah, and that's kind of the ultimate question, I think, and that's going into kind of the studies that I'm conducting at the moment, where I'm comparing the different types of mucus. So I have the F127 with mucin, I have F127 without mucin, I also have glycerol ethanol, which is sticky, and water, which is obviously not. So it'll be really interesting once this data comes out to actually see whether it is actually necessary or not. And if it's not, that's fine. At least then we know, we don't need to mimic mucus. It's not the end of the day, So yeah, like I said, it's just kind of waiting for the data to come out, but it will be interesting when we find out.
Okay, so thank you again, Lucy.
No worries. Thank you very much.